So let me see if I can find the examples I like down here. Oh, this is a nice divisibility one. So we'll continue talking about induction just for a few minutes, and then my goal also is to let you do some challenge problems. You know, maybe not give you a ton of time today, but I wrote a bunch up there, and I don't know what exactly. I didn't know how to divide them up. I just selected some, and in fact, there are others that I was just looking at, and I'm like, oh, I should have added 71 as well because I like that one. There are a bunch on there that I like. I just took a sample that are cool and fun. So, you know, I don't know, if you haven't yet done any challenge problems, and that's okay, I didn't technically ask you to do any yet, so. I gave to you before spring break thinking that, like, in Tahiti you might want to, like, on the beach, when you're bored, you just might want to do some challenge problems. Think about infinite series. So, anyway, if you haven't done any, that's okay, but let's maybe focus on these in the coming days. We have some delayed opening days and things like that. We have some squisher, and we're done with this unit teaching, kind of, but it'd be good for you to try some of those problems. So those are my suggestions as a sample. Some of those you've already done, I hope. I don't know. But I'll give you a couple days to do it. Okay, so let's turn our attention to something that doesn't have the same flavor as an inductive proof of the ones like we did yesterday. We did lots of series, and you're like, oh, okay, I get it. I always just like have this thing. I always replace a big part of it with the thing, and then I, you know, got this like kind of system now. I love it. Don't change anything, Mr. Chase. Okay, well, this is going to change things a little bit. Okay, here we go. So this is, again, let's back away from this statement just for a second and be like, oh, cool, we're going to be able to prove this. It's an interesting result. 9 to the n minus 1 is divisible by 8 for all n. Just in my head, I can't resist it. I got to check the first couple. Okay, not, yeah, 1 works, 2 works, 3, where's my calculator? Okay, so you can check it first couple cases. It would be remarkable if this was true, but we can convince you that it's true using a small proof by induction. So here we go. It's going to follow the same structure, right? Okay, so check n equals 1 is our first case, right? And sure enough, 9 to the 1 minus 1, which equals 8, is divisible by 8. Yay. Okay. Next, assume that 9 to the k minus 1 is divisible by 8. For some n equals k. All right, and then our goal is, you know, this is our claim. We claim what? 9 to the k plus 1 minus 1 is divisible by 8. Is that okay? Let's stop there and make sure everyone's okay. Is that okay? Is this frame, I mean, because even these statements is like maybe not as straightforward as yesterday, but this is the statement, right? And by the way, I know your book, I didn't really emphasize that notation yesterday, but I kind of like it. I mean, you're welcome to do that, right? Did you understand that P of k and P of k plus 1 notation yesterday in your book? Kind of taking a cue from like logic, right? Where you'd like say, what's P? It's a function? Well, no, not really. It's a statement, right? So just like you would do in logic, right? Let P be the following statement. Yeah. So hopefully you're okay with that notation. And in this case, you know, this whole thing is that like P statement, right? 9 to the n minus 1 is divisible by, sorry, not proof. Right, that's our statement that we're going to replace k with, and k plus 1 for n. Is it okay? All right, so I'm going to play around with this, and those who maybe had success trying this, maybe you figured this out. Okay. I don't know, is this the example that's in the book, or is it something similar? I don't know.
So you say check P1 and then assume PK and then...
No, I meant, is this particular 9 to the n minus 1? Is that their example? No, it's something similar though, or something. Okay, whatever. All right, so that's good. This example will be different than the one that's in the book. That's wonderful. Okay, you can look at the book for another one. But they take the similar approach, I think. So let's consider 9 to the k plus 1 minus 1. And my urge is, of course, like, and this part is certainly like our idea from yesterday. We would like to, like, go out of our way to use this assumption, right? Because this is a powerful thing. If we can know that for some k, this works, then let's use that, right? So motivated by that, I'm going to do a couple strange algebraic manipulations, okay? Ones you wouldn't normally do, is the point. So certainly, I hope you can agree with that. I think that's not too bad to swallow. We can break this 9 to the k plus 1 up into 9 times 9 to the k. All right, then the following trick is even more exotic, but let's see if I can convince you that you're allowed to do this too, right? This is 8 times 9 to the k plus 9 to the k, and then we still have a minus 1. And this is because 9 apples are equal to 8 apples plus 1 apple, right? I know this is a little weird for people, right? But isn't it true that 9x equals 8x plus x? Okay, I know that's weird, but... And again, why would you do that? Well, you wouldn't. You'd never do that. This is dumb, right? Except for what we're trying to do. We're trying to get this to happen, right? You see where this is heading? In fact, let's just stop for a second and stare at this until you have the epiphany. Did you see it yet? Don't yell it out. Let everyone have the epiphany. Here, I'll help. There you go. Have the epiphany. And once you have the epiphany, you're almost like, you're kind of like, oh, we're done. Right? Just by retooling this and making it look like this, maybe we can convince ourselves. You say bye. Maybe. What do you see, John? Figure it out? It's a multiple of 8. And? Yeah, so let's, I'm just going to write out what Jenny said. So actually, we can, I don't mind you writing words here. The words are good. You could make me take a slightly more formal approach, but I think this is the way we're about to write it is rigorous enough for our purposes. Okay, so here's our favorite word in math. Clearly, don't we like that word? Makes everyone who's reading it feel stupid. Okay, clearly 8 times 9 to the k is divisible by 8, right? And 9 to the k minus 1 is divisible by 8. By assumption in step 2, you know? So it follows that the sum 8 times 9 to the k plus 9 to the k minus 1 is divisible by 8, which is what we claim. Thus, the proof is complete. You can say something really triumphant like that. By induction, I guess we should say. Whatever, something, right? Okay, so something like that is fine. If you want to be slightly more rigorous and use like a slightly more algebraic approach to justifying the last piece here, you might say since being divisible by 8 means if you're divisible by 8, that means I can write you as 8 times q. Isn't that right? It's a little rude, but if you say you're divisible by 8, that means I can write you down as 8 times q, where q is some integer, right? Isn't that, if you say you're divisible by 8, right? So that is, couldn't we, if this is really divisible by 8, we could replace this with 8q, couldn't we? Right, so then that would be more clear. You could factor out an 8, If you wanted to say, for some q, this is 8q, for some q. Factor out an 8, and then clearly this is 8 times stuff, therefore it's divided by 8. You could be more formal. But this is good. I think this is pretty convincing to anyone who's reading it. What did you say, Andrew? No. By assumption here, right, that it was true for 9 to the k minus 1, right? That's exactly right. That's how we've done all the inductive proofs, right? Well, let's be careful. We're assuming that it's true for some k value, which does take the same form as this expression, but for some k value. And then we're proving that it's true for k plus 1 based on the fact that it's true for 9 to the k minus 1, right? Now, what if someone came along and said, hey, but it isn't true for 9 to the k minus 1? Well, then this wouldn't be, that it wouldn't be true for to the 9 to the k plus 1 minus 1, right? Right? This is like that, if A then B, right? And we checked it for the first case, okay? So, but this, you're right, this assumption is huge, right? Right? But it could be false, in which case this whole thing falls apart, which is fine, right? But it happens to be true. Boom, so we're done, you know? Yeah.
I still don't get why 9 is
No, replace 9 to the k with x or something.
Yeah, so this becomes this. Right, I'm just splitting it up using this rule. Right, replace x by 9 to the k with 9 to the k. Right, so this is 9x.
That's so smart.
Isn't it cool?
Yeah.
It's weird, right? It's a little bit of a. I mean, if you, right? What is this? Like, replace x over in this statement with 9 to the k. Wouldn't this say 9 times 9 to the k equals 8 times 9 to the k plus 9 to the k? Mic drop. Okay. Yeah, right? I mean, isn't that cool? I mean, it's weird, but it's a trick that I mean, again, no one would ever do this piece of algebra except to, like, do what we just did, right? To make this, that's like what we're doing, though. We're trying to prove a particular thing. So you know, if you want something to happen, make it happen. Okay, you want to start this for another second, or are we good? Notice again how many words I have. I think words are good. This is all about communication, right? I know it's true. You don't have to tell me. It's about convincing a reader, a skeptical reader here.
If the math is right, but the words are wrong.
Then maybe you lose some points. Yeah, I want a summary statement. I want some structure to it. I don't just want like algebra scrawled up the margin, right? I want like to communicate truth to someone. All right, the other kind of proof that you saw that I asked you to do one of, so I thought I'd show you a way to prove this. Would be a proof like this. So here's an inequality, n factorial is greater than 2 to the n. Notice again the initial condition, kind of like the warm-up. This is starting at 4, and it's not just for fun, it's because it's not true prior to that, right? Like 3 factorial is actually not greater than 2 to the 3rd. Yes, right. But then it starts being greater, which is cool. This actually ties back into like infinite series and stuff like that. Maybe you don't have in your heart an intuition as to how fast these two functions grow. Okay, but after 4, this dominates. N factorial, in fact, does grow faster. I mean, maybe you have that intuition already. That n factorials grow really fast, faster than exponentials even. But this is going to prove it for at least 2 to the n. It'd be kind of fun to prove this for b to the n. N factorial is greater than b to the n for some sufficiently large n. That'd be fun. Anyway, just thoughts in my head. Okay, proof by induction. We're going to say this in faith, hoping that we have one. Okay. So no, number 1. You don't necessarily have to, but a lot of times people will advertise that when they go to prove something by induction. Mainly so that, you know, or they'll say, in the following argument, we're gonna make an inductive argument of some kind. You know, they'll say something to cue people who are to cue mathematicians into me. Oh yeah, okay, I know what to expect then. So we check the base case, and that is n equals 4, right? And sure enough, 4 factorial, which is equal to 24, is that greater than 16? which is equal to 2 to the 4th. Right? Check. All right. And then we assume for some n greater than or equal to 4 that, excuse me, k. We like to use a different letter. That k factorial is greater than 2 to the k. And again, we will prove that k plus 1 factorial is greater than or equal to 2 to the k plus 1. All right, so that's what we're about to do. Okay? So, oh. Yeah. Good catch. All right. So, yeah, how are we going to do this? I mean, yeah, just for the sake of variety, I think I'm going to show you a slightly different approach on this. Maybe starting with the following, right? So I know that what we've been doing is like we start with the left-hand side, we play with it until we can like use the assumption to, right? And then, so, but maybe what we could do, because we can't work with this inequality as if it's true, because it hasn't yet been established. But we can work with this inequality, right? Because we're taking it to be true, right? This one we can't take to be true yet. But this one we're taking to be true. So we could actually take this inequality and do stuff on both sides of it, right? You want to add 50 to both sides of this inequality? Knock yourself out, right? You can do that. You want to multiply by 5 on both sides? Sure, right? This one, no, don't do that, right? But this one we could. So this is a little bit of a different, maybe a little bit of a different approach. I don't necessarily, you could start with this too. You just have to be careful. You have to start with this side and like work with it only until you get to something that you can convince yourself is greater than 2 to the k plus 1. But I thought just for fun, we'll start with this assumption. From the assumption we have k factorial is greater than 2 to the k. And since we're taking that to be true, we can do stuff to both sides. What might you like to do to both sides? Add 2. Multiply by 2 would be a fine way to do it. Yeah. Or multiply by k plus 1. Either one actually would be a good argument. My first inclination was to multiply by k plus 1 on both sides. But I think it would be fine if you multiply by 2 on both sides too. Okay. Everyone, 2 to the k. Excuse me. So far so good. This is an inequality that's true. So this must also be true. If this, then that. Yeah, but we can say that this is greater than 2 to the k times 2, right? Which is equal to 2 to the k plus 1, right? This last statement, let's make sure we describe to the reader, because aren't you confused why I can do that? Yeah, exactly. I thought so. So we need to say something about why this is true, right? So you should say it, right? Don't just write this and assume we know. This last statement, don't be afraid to write English words, holds because k plus 1 is greater than 2, right? Isn't this okay to do? To replace something, k plus 1 is bigger than 2, isn't it? So can we replace k plus 1 by 2 and have this inequality still work? That means since k plus 1 is greater than 2, right, this quantity will be greater than that quantity. And why do I know that k plus 1 is greater than 2? Because I told you so, right? Right. Since k is greater than or equal to 4, right? And then we should say some summary statement then too when we're all done. But we are all done, kind of, right? Yeah, Josh? Yeah, actually, you could actually, this could be your proof right here, just this one line, right? Yeah. This is greater than, well, we have to be a little careful. Yeah, I might also add that k plus 1 times k fact. Yeah, yeah, you could clean this up. You'd have to write, it'd be basically the same thing, right? So you could say k plus 1 factorial equals k plus 1 times k factorial, which is greater than k plus 1 times 2 to the k. And this piece here is because k factorial is greater than 2 to the k by assumption. Right? But if you're trying to work just with this, like, if this is equal to this, which is greater than this by assumption, because of this, which is greater than 2 times 2 to the k, which is equal to 2 to the k plus 1. And so something like that, right? And again, this here we'd also have to justify because k plus 1 is greater than 2 because of what we said here, right? So I mean, there are other ways you could write this, is the point. Let's say you need to make some of these arguments, right? You know, so the statement holds for all n, right? So n factorial is greater than 2 to the n for all n greater than or equal to 4 by induction. Black box. Okay. Yeah, right. Yeah. Yeah. Here, try 0.5 factorial on your calculator. It won't do 0.75 though. Yeah, for all, yeah. And in this context, and because we're using n and k, we'll do all fast and just figure out. Maybe we should say that. Where? For all natural numbers, n greater than or equal to. Like on the warm-up, I didn't say that, right? I said n greater than or equal to, n greater than or equal to 2, but probably should have said all natural numbers for 10. Oh, about factorial of like a thing besides positive numbers. Huh? Oh, you can actually. Your calculator just doesn't know how. Your calculator knows how to do all the multiples of a half. Because they're nice. They work out nicely.
This one is so okay. When you have 4 factorial, for example, right? You did 4 times 3 times 3 times 1, right? And then what happens when you do 0.5 factorial? You do 0.5.
No, but you're still looking for something that such that 0.5 times the factorial for it, which would be negative 0.5, right? Factorial. That still equals 0.5 times negative 0.5 factorial, right? Like that property that n times n minus 1 factorial equals n factorial still has to hold, regardless of whether n is an integer or not, or a complex number, right? I don't know off the top of my head, but it's not nice. Right?
What's negative 1?
But you can do a complex number factorial. You just have to do, you have to use something called the gamma function. But now we've gone too far afield. Go look up gamma function and you'll have a table. I don't know if that's it. It's not nice. No.
Because like there's 0 factorial.
But then it has to be backwards.
Because
you have to carry through all the way, right?
I see, I know.
Yeah.
I didn't do 0 factorial because 0 times negative 1 factorial.
Yeah, so whatever negative 1 factorial has to satisfy that.
But
Stop talking about this. Okay, I will talk about this if you come by sometime. Okay, because I can actually give you, especially if you know a little bit of calculus, I can give you a definition of the gamma function, and we can work it through. Here's one that I thought I'd just leave in your head too, as you leave. This is, oh no, where is it? I have it somewhere. This is kind of a fun one that. I thought I'd put up here just to show again that you can prove other interesting things using induction, right? Here's like a fun problem, right? Oh, I'm sorry, that should say 2 to the n by 2 to the n grid. So if you want like something to stew on,
So I think I changed 4 because you can always divide it into smaller grids until you get a grid of 1 by 1 or 2 by 2.
kind of, you should draw a picture for me.